everyone, this is a problem solving session for week 8. In this lecture, we will talk about optimization problems, and then we will move to Newton's technique, and in the last part, I will talk about derivatives, okay? So let's start with the first example, which is an optimization problem. Here what we have, first we need to understand the problem, and then we will try to create a function to be optimized or minimized, depending on the question. Okay, we have a dog named Cooper here at the beach, at this corner, and we throw a tennis ball towards the sea, and Cooper tries to catch this tennis ball. And there is this information about Cooper. He can run on the beach with this velocity 6 meters per second. Let's write this down as an information. Okay, Cooper can run at the beach with the velocity of 6 meters per second, and it can swim in the water. The velocity of the dog in the water is given as 4 meters per second. Okay, 4 meters per second. And what we want to find here is, we want to, by the way, there is also extra information here. We throw the ball far up 30 minutes and in the sea, and 10 meters far into the sea, like this. And then what is the question? We want to find the time that is needed. In fact, we want to minimize the time where Cooper should jump into the sea. So the question is about this point where Cooper jump into the sea so that it catches the ball in a minimum time. Okay, we want to understand this point, where to choose this point so that dog catches the tennis ball in the minimum time. Okay, so let's start decorating the picture. Let's say this distance is x, and then of course this part should be 30 minus x. Here this is given as 10, and then from here to here, this distance, which is the hypotenuse of this right triangle, is, by using the Pythagorean identity given by that, we have this velocity 4 meters per second in the sea, and we have this velocity 6 meters per second in the on the beach. Okay, let's use blue color for the velocities. And what we want to maximize or minimize here is the time. We want to minimize the time that is needed. In fact, we want to find this point where the dog Cooper should jump into the sea to minimize the time that is needed to catch the ball. Okay, so we want to minimize the time. That's why we want to write a function of it in terms of our unknown variable x. So this time is in fact given by the time spent on the beach plus the time spent in the sea. Okay. You know, we have this usual formula from physics, says that the distance is always constant velocity times time. That's why the time spent on the beach can be found by dividing this distance 30 minus x. Okay, let me also put that distance to here. 30 minus x is the distance. If we divide it by the time, if we divide it by the velocity, sorry, we don't have the time, we just have the velocities. Let's call this velocity as v1 and this velocity as v2. If we divide this by the velocity, which is 6, I obtain the times that is needed to travel this distance on the beach, right? Similarly, this is the distance covered in the sea, given by this expression. If I divide it by the velocity there, the velocity in the beach, which is 4 meters per second, it will give me the time spent there. Okay, time is always distance divided by the velocity. Okay, this is our function to be minimized. By the way, let's also give the upper and lower bounds for x. I named x as the distance from this point to the ball, right? So x can be at least 0 And x can be at most, of course, 30. Okay, these are the upper lower bounds for x. And then, so this is our optimization problem. We want to minimize this function, which is the time function. Let's take the first derivative of it to find its critical points. Okay, here you can separate this expression like 30 minus 6 minus x minus 6, right? Or instead of writing over a common denominator, you can write it like that. 30 minus 6 is just a constant. It is gone after taking the derivative. So this is the derivative of the second part as its coefficient. Now look at the second expression. We need to take the derivative of square root of 100 plus x squared. 1 over 4 is just a constant there. Just take the derivative of square function. It goes like 1 over 2 times square root itself. Okay, I am applying the derivation rule for square root now. And then you need to multiply with the derivative of this insider part, which is 2x. And then you can simplify things like this. Okay, and then if you write this expression over a common denominator, the most compact form of the first derivative is given like this one. Minus 2 100 plus x squared divided by this common denominator, I guess. Okay, like this. Now we are ready to find the critical points. Critical points are the points at which the first derivative is 0 or the first derivative is undefined, right? The first derivative is 0 when, look at the denominator, please. If you have this, you will obtain first derivative as 0, right? Like that. Okay, let's solve this equation. If take the squares of both sides, please. Then this is 4 times 100 plus x squared. And then you can easily solve this equation for x. 5x squared is 400, x squared is 80. Then x is plus minus 4 square root 5, 4 times square root 5. And as you know, x is the length. X is a number between 0 and 30, so you can not take a negative value for it. You will just eliminate this and you can take this one as one of the critical points. Is there any point where first derivative is undefined? Look at the denominator. Can you find any value for x which makes the denominator 0? Since x squared can never be minus 100, it can never take minus values. There is no points where first derivative is undefined. Okay, the only critical point is this one then. Now, we need to prove that this critical point gives us the possible minimum value of the time function. You can use sign tables to prove such things. For example, let's create a sign table for the time function. So we just have one critical point. And if you remember, 30 was the upper bound. Now I will look at the signs of the time function, and then depending on the signs, I will comment on where the original function t is increasing, where it is decreasing. Okay, what we know is first derivative is 0 when x is 4 times square root 5. If x is between 4 times square root 5, you know, you can just understand the sign of the first derivative function by just picking up some value like 1 here, insert 1 to everywhere, and you will see that first derivative function will get negative values. If x is more than 4 square root 5, this part will be obviously positive. You can verify this by picking up a random value from this interval. And then what about the time function? If the first derivative is negative, time function will be decreasing. If the first derivative is positive, time function will be increasing, meaning that right at this point you have a minimum value, right? This proves that This critical point gives us a minimum value so that I can write the conclusion as t attains, time function attains its minimum value at x equals 4 square root 5. Then, what is the answer of our problem? What was x? X value was here, the length from ball to here. So we were searching for this point at which the dog Cooper should jump into the sea. Let me draw that picture here again. So here the dog Cooper starts running at the beach. There was this point at the beach where the dog Cooper jumps into the sea, and then he catches the ball. And we solved for x, right? X is 4 square root 5, which gives the minimum value for the time function. Then this length here is, remember, from here to here, it was 30 meters. Then this part become 30 minus 4 square root 5. And yeah, that's it. This is the answer. The dog should jump into the sea right at this point where the length is this much, okay? This minimizes the time. Jumping point should be right at this distance from the starting place. Okay, so that's it. Let me just go over the steps. To be able to solve the optimization problems, first thing to do is to create a function depending on just one variable. This function will be the function that you want to minimize or maximize, okay? In this case, we wanted to minimize the time function. That's why we try to construct a time function depending on the variable x. And then the next step is taking the first derivative with respect to its variable so that you can find the critical points. After finding the critical points, then the third step will be proving that that critical point gives you what you want, like maximum or minimum depending on the question, and you can prove that by creating sign tables, because in those tables you see that where your function decreases, where it increases, so that you can understand whether your critical point is a maximum or minimum. Okay, let's move on with the next example, which is again an optimization problem. Here what we have. Okay, we have a 3-meter wall shown here, okay? We have this wall, and it's 8 meters from the building. This wall runs at 8 meters from the building, like that. And the question is, find the length of the shortest straight beam. Okay, we have a beam like that. We are interested in the length of it, and we want to minimize the length of this beam. So what we are interested here is the length of this beam, and we want to minimize the length. The question is, find the length of the shortest straight beam that will reach to the side of the building from the ground outside the wall. So we want to put a straight beam like that is touching both ground and the building and going over the wall like that. So we want to minimize the length of such a beam. Okay, let's try to find a function for this length. For example, we can decorate this length as x. Obviously, it is related because you can put your beam in that position, or you can lean it like this, or you can lean it like, or you can, wait, I should be more careful. You can lean it like this, more vertically. So the length obviously depends, the length of this beam obviously depends on the place where you put it at the ground, right? That's why we should decorate this part as an unknown. Okay, and then let's try to construct a function for L depending on x. Let me also call this part as y. And after decorating like this, you understand that we need to use the similarity of triangles, right? To eliminate one of the variables. But first, let's express L in terms of the new variables that we put in our picture. Obviously, from the Pythagorean identity, L square is x plus h square plus y square. Okay, we created a function for L, the length of the beam, but in this form, we cannot optimize it because it depends on two variables, right? So we need to eliminate one of the variables in terms of the other so that the function for the length of the beam, the L function, will depend on just a single variable. Only then you can take its first derivative and start your optimization. So how to express one of the variables here, x and y, in terms of the other? By using, of course, the similarity of triangles. So you see here, right? We have a triangle like that, and here is x, 3, 8, y, and the similarity works like x over x plus 8 is the same as 3 over y. Okay, let's use this. Similarity of triangles. Okay, so x over x plus 8 comes from taking the ratio like that, is the same as 3 over y. And from this equality, you can solve y in terms of x easily. It is 3 times x plus 8 divided by x. You see, by inserting this value to here in your formula, you can eliminate y, and then L will just depend on x. Okay, let's insert it. Then the function L becomes x plus 8 square plus this square, right, which is inserted for y. Okay, like that. Now, this is a valid form to optimize because it just depends on a single variable. Just x. Okay, now we are ready to take its derivative, but before taking the derivative, maybe we can just rearrange the terms here so that taking derivative operations would be easier. But we have here then 1 plus 9 over x squared, I guess. Okay, this is the function L square. Now let's take the x derivative of both sides. 2L L prime is whatever you have on the right hand side. You know, this is the product function, and to take the derivative of it, you need to apply product rule. So it goes like derivative of the first expression, 2 times x plus 8 times the second one, 9 over x squared, plus first expression stays the same times the derivative of the second expression, which is minus 18 divided by x cubed, right? Okay, so this is the derivative of the right-hand side. And then let's try to make rearrangements on the right-hand side so that we can find its compact form. Okay, let me do it like that to save some time. 2L times L prime is, if you do your computation on the right, you will obtain this compact form. X plus 8 times 2x cubed minus 144 divided by x cubed. Okay, and now we want to find the critical points of the L function. That's why we need to solve this equation for where L prime is 0 and for where L prime is undefined, okay? So L is a length. That's why it can never be 0. That's why to make L prime 0, you need to look at the right-hand side, okay? Right-hand side becomes 0 if x equals minus 8 or from here, if 2x cubed is 144, which means x cubed is 72 and x is then 2 times cube root of 9. Okay, so you know, x is a length and it can never be minus. That's why I will directly eliminate that, which gives us the only critical point as this number. Okay, this is the only critical point. Only critical point is this one. And is there any point where L prime is undefined? So you see L prime is the expression on the right hand side divided by 2L, where L is never 0, right? As it's a length. That's why the denominator can be 0 only when x cubed is 0. So this becomes undefined when x is 0. By the way, this is also a critical point, right? Let me also move the only word. Okay, now it is time to construct its sign table here. Okay, so 0 is here as the end point of your interval because x can never be negative values. It also appears in the critical point list. So this is the critical point, and then L prime, I am constructing the sign table now, and L. You know, L prime is 0 here, and if you choose a number between 0 and this number, like you can just choose 1, you will see that L prime takes negative values, and after this number, you can also comment according to this phrase. If x is greater than this cube root, then this will exceed this number so that you will get positive values. If x is less than this number, this part will be smaller than 144 and you will get negative values. If first derivative is negative, original function is decreasing. If first derivative positive, original function is increasing, so that right at this point, at this critical point, you have a minimum value, right? So your conclusion is L, the length of this beam, attains its minimum value when for x equals this number. Okay, so this is the ultimate answer to this question. We were searching for the point. We were searching for the shortest length of this beam that will reach to the building from the ground, and the length becomes shortest if you choose the x length here as this number. Okay, so this is the answer. Let's look at the next example and then we can take a break. Okay, next optimization example is a real life problem about cinema theater saloons. Okay, cinema theater. So what do we have here? A movie screen on the wall is 6 feet high. You know, this part is the movie screen. From here to here. Let's say movie screen. Okay. And it is placed at 10 feet above the floor. You can see it is given as, and it is placed at 10 feet above the ground. Okay, let me color the movie screen in red like that. And the question is, at what distance x from the front of the room? X is the distance of your seat to the movie screen. Should you position yourself so that the viewing angle of the movie screen is as large as possible? So, you know, now you understand why I call it as a real life problem, because after solving problem, you will know where to sit in a movie theater to make your viewing angle as much as possible, okay, to maximize your viewing angle, where you should sit. This is the question, because the viewing angle of the screen directly depends on where you sit, right? For example, if you sit closer, then the viewing angle will change, right? If you sit like farther distance, the viewing angle will change again like that. Okay, you see how much does it change depending on the position of your sitting place? So it keeps changing. This angle theta keeps changing depending on where you sit. So we want to maximize this viewing angle. So where we should sit to maximize this viewing angle theta? This is the question. That's right. We want to optimize the viewing angle theta. We want to maximize the viewing angle theta. That's the question. That's why we need to construct a function for theta, for the viewing angle, depending on this variable x, where to sit to maximize. The question is where to sit to maximize theta. This is the question. Okay, can we create a function for theta depending on x? That's the problem now. Okay, so x is this edge, and how do you relate the length of the edges of a right triangle, for example, to the angles inside this triangle? For example, concentrate on this right triangle, and let's call this angle as beta. How can you relate beta to x? Beta is an inside angle of this triangle, and x is the length of the adjacent edge. How do you relate them? So here is a relation. You know, trigonometric functions relates the angles with the edges of the triangle. So tangent beta is in fact opposite edge divided by the adjacent one, which is given as x. And similarly, let's call this angle as alpha, and then tangent alpha is expressed as the opposite edge, which is 30, divided by the adjacent edge x. Why do I invented alpha and beta? Because somehow I want to relate these lengths 20, tan x to the angles inside the triangle, and that relation is given by the tangent function for us. And then how do you, okay, we obtain some relations between beta and x and alpha and x, but what we are interested in, the theta, right? We want to construct a function for theta. That's why now we need to invent one more relation between theta, alpha, and beta. So theta is, in fact, alpha minus beta, right? Okay, theta is given as, obviously, alpha minus beta. And let's insert the expressions that we found for alpha and beta to this function. So that's why we need to solve for beta and alpha from these two equations. Can you solve them for the angles? Of course, because we know an inverse trigonometric function that will neutralize tangent, right? If you apply arctangent to both sides from this equation, these equations, beta can be solved as arctangent of 10 over x, and okay, let's write beta as arctangent of 10 over x. Why? I applied arctangent to both sides to get rid of tangent function on the left. And similarly, alpha is arctangent of 30 over x. Okay, then let's insert these two expressions to here to obtain an x-dependent function for theta. Alpha is given as arctangent, and maybe I should keep using colors. Arctangent 30 over x, and beta is given as arctangent 10 over x. This is beta. This is the function of alpha. You see, we obtained here a function of theta depending on just x. And what are the boundaries for x? Obviously, since it's a length, it should be a positive quantity. And as I showed you, like at the beginning, you can just sit wherever you want. Let's put the upper bound. You can keep getting far away from the screen, so you can just give this upper bound. We don't know how big is the movie theater, so I will just put it infinity for the upper bound. Okay, then next step is to taking the first derivative. Constructing the function to be maximized or minimized. This step is done, and we want to maximize this function. To maximize it, first we need to find the critical points, and then by using sign tables, you can prove that the critical point that you found is in fact gives you the critical point that you obtain in fact gives you the maximum possible value. Okay, let's first handle taking the first derivative. Okay, what is the derivative of arctangent function? Its derivative goes like 1 over 1 plus x, whatever you see here, you will square it, times the derivative of the insider part. What is the derivative of 30 over x? It is minus 30 over x squared. Similarly, here the first derivative of arctangent is 1 plus square of whatever you see inside. And you will multiply it with the derivative of this insider part, which is minus 10 over x squared. Okay, then what we have for the first derivative? We have minus 30 over x squared times, okay, you can just compute this square here and then arrange the terms to obtain this quantity. 900. And then similarly, you will have 10 over x squared times x squared over x squared plus 100. You have simplifications. This is gone. These two are simplified. So what we have here is minus 30 over x squared plus 900 plus 10 over x squared plus 100. And if you write this expression over a common denominator, what you obtain? What we obtain is the following. We have this common denominator times x squared plus 100, and in the denominator then we will obtain, if you do the computation, you will get this number minus 1x squared. Okay, after this step, you can search for where the first derivative is 0 and where the first derivative is undefined. Let's search for this case first. The first derivative function is 0 if 20x squared is 6,000, meaning that x squared is 300 and x is 10 squared 3 or minus 10 squared 3. As x is a length, remember x is the distance from your seat to the screen. So x is a length, and it can never be negative. That's why you find this critical point here. Is there any point which makes the denominator 0? As x squared can never get negative values, no point coming from here. So this is the only critical point for us. Okay, then we need to prove that this critical point maximizes the viewing angle. How do we do that? We will construct a sign table. This is the last step. Okay, so let's construct a sign table for the function theta, first derivative. Its critical points are, okay, x can never be negative, so that's why I start this table from 0. The critical point that we find here is 10 squared root 3, and it can take any values then till infinity. So first derivative becomes 0 at this critical point. If you choose a smaller number than this, then you will understand this denominator becomes less than 0, right? It becomes positive because we are choosing a smaller value than 10 times square root 3. So this quantity is positive. If you choose a bigger number, the quantity will be negative, meaning that since the first derivative is positive here, original function is decreasing, it is negative here, original function here, it is increasing, decreasing. So this point gives you, in fact, the maximum value. This sign table proves that theta attains its maximum value at x equals this number. So after seeing this solution, after we solve this optimization problem together, if you go to the movie theater, you know where to sit to maximize your angle theta. So this x, the distance from your seat to the movie screen, should be exactly this number to maximize your viewing angle. Okay, after going over the steps again for this solution, I will take a break. So what we did here, we first try to construct a function, construct a function expression for the theta that we want to maximize. So we construct a single variable function for it, and then by taking the first derivative, we search for the critical points, and then you have to prove that whether your critical point gives you a maximum or minimum, and you can do that by creating sign tables like this. Okay, I stop here for the first part.